All right, the next convergence test we're going to consider is the ratio test. And you'll find this in section 9.5 in our textbook. And a note here, we're going to skip the root test and the various comparison tests that you'll also find in this section. We're only covering the ratio test here. And so what does the ratio test say? It says that for the series of a sub n, let r equal the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n. Then if this number r is strictly less than 1, the series converges. If this number r is strictly greater than 1, the series diverges. And if r is equal to 1, this test is inconclusive. Okay, you have to try something else in this instance. It turns out that there are series with r equal to 1 that converge, and there are other series with r equal to 1 that diverge. Okay, so knowing that r is equal to 1 alone is not sufficient to conclude whether a given series is convergent or divergent. You have to do something else. All right. Now note that this result looks really similar to our results on geometric series. Okay, there we know that a geometric series with common ratio r will converge if r is less than 1 in absolute value, and it will diverge if r is greater than or equal to 1 in absolute value. Okay, so it's that result on geometric series that lies at the heart of the proof of the ratio test. The rough intuition here is that since this ratio in absolute value is approaching this number r, our given series, at least its tail end, will look like a geometric series. And from that fact, these results follow. Okay, so I'll go ahead and just sketch a proof. Okay, we're not going to include all the details here, but here again, since r is the limit of this ratio in absolute value, okay, at least for sufficiently large values of n, that implies that a sub n plus 1 in absolute value is approximately equal to r times a sub n in absolute value. Just think about multiplying this a sub n over, and again, since r is the limiting value, this is why we don't see an equal sign here. But again, for sufficiently large values of n, this will hold. All right, so this implies that the tail end of the series of the absolute value of a sub n will look as follows. Okay, so there's some index capital N such that for all terms of our sequence a sub n, okay, this relationship will hold for all terms either equal to capital N or past this index capital N. Okay, so looking at this tail end then says the following. A sub n plus 1 in absolute value, well, that's approximately equal to r times a sub capital N in absolute value. Now for a sub capital N plus 2 in absolute value, well, again, this relationship will hold. So it's roughly r times a sub capital N plus 1 in absolute value. But this thing, as we just noted, is roughly r times a sub capital N in absolute value. So you put those two together, and you get the a sub capital N plus 2 in absolute value is roughly r squared times a sub capital N in absolute value. Okay, and then you get an r cubed times this absolute value term, so on and so forth. Okay, so this thing, in fact, is equal to a sub capital N in absolute value times, and you see here, this geometric series in parentheses, right? And so it's the convergence and divergence of this series that will give rise to these results. Now, again, I'm omitting lots and lots of details here, but this at least gives you, a flavor of what exactly is going on here with this result and how it relates to what we've already seen with geometric series. All right, so now let's go ahead and look at an example. So let's look at the series where we're summing 1 over n factorial, and here n starts at 1. So 1 plus 1 over 2 factorial plus 1 over 3 factorial, and so on. So here, a sub n is just 1 over n factorial. So a sub n plus 1, well, that's 1 over n plus 1 factorial. And so if I look at this ratio, I'm looking at 1 over n plus 1 factorial over 1 over n factorial, which simplifies to n factorial over n plus 1 factorial. Also note that since a sub n is positive for all n, these absolute values are actually not completely necessary, but I'm going to include them anyways, just because that's what you see in the statement of the ratio test. And a few examples we'll see in the next video, a sub n can take on negative values, and so there it'll become more important. But in any event, let's go ahead and simplify now. So n factorial, that's 1 times 2 times 3 all the way up to n. N plus 1 factorial, well, that's 1 times 2 times 3 all the way up to n, and then we just get this one additional factor, which is n plus 1. And so now we can go ahead and simplify, divide out, and we get 1 over n plus 1 there for this ratio and absolute value. And so r, which is the limiting value of this, this quantity, is equal to 0. And so, since r is strictly less than 1, we conclude that this series converges by the ratio test. All right. Now, this happens to be a rather important series. As we'll show in Chapter 10, this series actually converges to the number e. Okay, so nice little preview there. But that's a good place to stop. In the next video, we'll look at some additional examples illustrating how the ratio test can be applied. All right, thanks so much.